All right, good morning, good afternoon, good evening, ladies and gentlemen. Welcome to this series of tutorials. If you haven't already subscribed to the channel, leave a like, comment, and share. Now, in today's video, we are going to look at a very interesting theorem, or rather an inequality, and that is Gronwall's inequality. Now, this inequality is very important in the circles of differential equations in general, because it can be used to show that a system of differential equations are bounded. Okay, so I am basically using this inequality in my thesis, where I am also proving that my delay differential equations are bounded. So I just thought of sharing the proof, and I hope you can follow through as well. So the theorem says, suppose we have a finite time starting from a to some time before infinity, in which alpha, beta, and u are real valued continuous function, with beta of t being greater than or equal to 0, and the negative parts of alpha are continuous, and u satisfies this inequality. Okay, and if u satisfies this inequality, we can conclude that u is bounded. Okay, and that is, if you observe this part of the inequality, we do not have any u terms, so meaning that when we solve this integral here and we simplify, we're just going to have a constant. Okay, so u will be bounded by that constant. So basically that's what we do. Now, the setup for Gronwall's inequality, for you to show boundedness, for instance, in my case, for differential equations or delay differential equations in my case, you sum all the parameters, okay? You sum all the parameters and try to come up with this inequality here, okay? And that is, of course, the parameters of the population are all going to be continuous, and that is generally what is expected. So you try to come up with this inequality here. Then if you come up with this inequality, then you can show boundedness by simplifying this inequality down here. Okay, so that is the setup for like real world problems. So in my case, in this proof, I'm just going to show you that given this, and we are satisfying all these conditions in terms of alpha and that being continuous, then we can have this at the end of the day. Okay, so let's do that. So we're going to assume we already have u in this form, and we've already proven that beta of t is greater than or equal to 0, and we've already shown that alpha of t is continuous. Now, how do we progress from here? We're going to consider an initial value problem, y prime of t equal to beta of t and u of t, with an initial condition of y being equal to 0. So we consider this initial value problem where beta of t is the same beta of t that we have here, and u of t is this u of t that we have here. So now, if we simplify this initial value problem by integrating both sides in some interval t, say a to some time t, for instance, let me say time t. When we integrate both sides, we have a to t y prime of t equal to the integral from a to t. We'll change this to beta of s u of s ds. What we observe on this side of the equation is that we're going to have y of t minus y of a by the fundamental theory of calculus. Okay, when we integrate, it just be y, then we plug in the upper limit and the lower limit, and this side we're going to have a t beta of s u of s ds. Okay, so now that we have that, we know that this is 0 by the initial condition, so we have y of t being equal to the integral from a to t b of s u of s ds. Okay, so we have our y here. Okay, let me put it in bars like that. Then we also have our y prime. I'll also put it in bars, y prime, which is equals to beta of t u of t. Okay, so we have this, and we also have our u that I'll write down here. Let me write it down. We also have our u of t, which is less than or equal to alpha of t plus integral from a to t u of s beta of s ds. Okay, so we have that. So this is where I would say the proof mainly starts if you have this. Okay, so this is mostly what we're going to use from here. So one thing you observe is that when you multiply throughout by, let's say, beta of t, beta of t, beta of t, okay, you observe that this part is just y prime of t. Okay, this is just y prime of t, because y prime of t is equals to beta of t u of t. So you can literally write this as y prime of t less than or equal to beta of t alpha of t plus beta of t integral from a to t u of s beta of s ds. So you have this. Then again, looking at this closely, you observe that this part is just y of t. Okay, meaning that you can replace this part with y of t, and you would have your y prime of t being less than or equal to beta of t alpha of t plus beta of t. Then we have our y of t. So I'm going to call this equation 1 because it is the most important equation in this proof. But more important than this equation is when we roll back to y prime of t as beta of t u of t, we put that here, beta of t u of t, and we have less than or equal to beta of t alpha of t plus beta of t y of t. Okay, if we replace that back, if we replace beta of t, we see that if we divide by beta of t both sides, we're just going to remain with u of t less than or equal to, here we just have alpha of t because the beta will cancel the beta, and here we're just going to have y of t. And I'll call this equation 2 because what we just need is y of t for us to prove this relationship, for us to come up with this, you see? So we see that y of t should be in some form of this part here because we already have alpha of t and u of t there. So how are we going to get y of t? Y of t will be obtained from this here, equation 1. Okay, so simplifying equation 1, we get y of t. And we see that equation 1 is some form of linear differential equation here. So if we group the parts that have y of, let's say y of t, I would say y prime of t, and this part becomes minus b of t, beta of t, y of t, being less than or equal to this part here, beta of t, alpha of t. Okay, so basically if we solve for y of t from this equation and replace here, we are done with the proof, right? So we see here that we can have some form of integrating factor. So I'm going to introduce an integrating factor mu. I'm going to introduce mu of t being equal to integral for negative, I would say a to some time t, okay? Then we'll say beta of r dr, okay? So I have this integrating factor whose derivative is equal to, remember, differentiating the exponent is just differentiating the power. So if we differentiate the power, that is an integral, this would just be the function here with respect to time. So it will just be beta of t like that, and we write back the exponent. So this would be negative actually. So this would be negative beta of t. Then from a to t, beta of r dr. So we have that. And when you look closely, this is just mu of t. So we can simply say mu prime of t is equal to negative beta of t mu, like that. Okay, so let's multiply throughout with the integrating factor here. We multiply throughout by mu of t. We are going to have y prime of t mu of t minus beta of t mu of t y of t, like that, less than or equal to mu of t beta of t alpha of t. So we have something like that, and we immediately recognize that this is a product rule. So that is dy of t mu of t dt. Okay, that is when you differentiate with respect to y with respect to time, you're going to have y prime of t mu of t, and when you differentiate mu, remember mu is negative, mu prime will be negative beta of t mu of t, which is just this part here. So it will just be that product rule here. So we see that, and this is less than or equal to mu of t beta of t alpha of t. Okay, and of course we want to cross multiply by dt, so that we have dt, so that we have dy of t mu of t here less than or equal to, so this side will change everything to u, so that we have let me write it like this. So to the beta of u alpha of u mu of u then du. Okay, then when I integrate on the interval a to t on both sides, what we're going to have is the following. So this side will have from a to t beta of u alpha of u. Then we can replace back what this is. So this is e to the negative a to u, so beta of r dr, like that, and we have du this side, and this side will just be y of t mu of t. Okay, that is because, remember, when we integrate this part, we're just going to have y of t mu of t minus y of a mu of a, but y of a is 0, so meaning that we're just going to have this part here, which is this part here. Okay, so that is just a brief background on that. Then we can consider the inverse of this. So y of t will be less than or equal to the inverse of this being multiplied here. So I'll say integral from a, because it's a constant, it's with respect to t, and here we are just with respect to u, so it can go inside the integral here and it wouldn't affect anything. So it'll be a to t b of u alpha u, this is mu inverse of t, then we have e to the negative a u beta of r dr. I'll put this in brackets and we have du here. Okay, now what is mu inverse? So remember, mu of t is equal to e to the negative a to t beta of r dr, like that. So the inverse will just be multiplying the power by a negative, okay? And this will just be positive. So the inverse of mu is just that. So now multiplying that by this, so we have same bases here. So we see that the powers will add. So basically mu of t times mu of t, I would put it. Yeah, mu of t times mu of t. With this being the other mu of t, I would put mu naught of t, something like that. We see that this will be, for this part, a to t. Then we have minus a to u beta of r dr. Okay, and we can change the signs here. So if this becomes positive, then we can change this to u and this changes to a. Okay, and basically we can see that by the fundamental theory or the fundamental property of integrals, if we write this like this so that you can see it properly, let me write it like this. Okay. Moving from a to u, then a to t is just the same thing as moving from u to t, then beta of r dr. So this simplifies to that, and we see that our y of t is basically less than the integral from a to t beta of u alpha of u. Then in the brackets here we have this, we've simplified, so it will just be e to the u to t beta of r dr and du here. Okay, and we have our y. So now, since we have our y, we know that our u of t is less than or equal to alpha of t plus y of t. This is from equation 2. Okay, from equation 2 up here in red, I think. Yeah, from equation 2 here, it's in blue. So we can just replace back and we have our bound. So we have our u of t being less than or equal to alpha of t plus our y of t is this one. So we have a to t beta of u alpha of u in brackets e to the integral from u to t beta of r dr, then RDR, then du, and we're done. So this proves Gronwall's inequality. So if you have any questions, you can leave them in the comment box. But for now, this is it. Have a great night. Have fun applying this.